Welcome back. We're now going to cover some of the technical background that is required for this course. We're not going to be able to cover everything, and of course there'll be many topics that we develop as we need them. But this is quite a technical course, and the main tool that we're going to use, or the main suite of tools that we're going to use, are those from linear algebra. So we need some more theoretical concepts, but we also need some more applied concepts from numerical linear algebra. Again, I won't be able to cover everything. I'm going to give a few references as well that you can look into yourselves. Also, we need some basic ideas from multivariable calculus and also some basic understanding of algorithmic complexity. So I'm going to talk about the first two topics and mostly spend time talking about the concepts that we need from linear algebra, or rather the concepts that I consider as background. We're going to be developing some more of these as we move along. So let's start from the very beginning. Linear algebra studies vectors. So we're going to be studying vectors typically in n dimensions. And the notation that I'm going to use is Rn or Rd. So what this denotes, if I write that V is an Rd, what I really mean is that V has D components, V1 all the way to Vd. If it's an Rn, it has components V1 all the way up to Vn. Concepts of linear dependence, linear independence, span, and basis are very important, and they pervade much about what we're going to talk about. It's easy to illustrate these in two dimensions. Here are two vectors in R2, U and V in R2. And you can see that there's no way to combine U and V in order to get, there's any place that you want to get to on the plane, you can take steps in the direction U and V and eventually get there. It's easiest for us to think about taking steps aligned with the coordinate axes, but we don't need to do that. So first point here is that U and V span R2. So mathematically another way to write this is, for any vector, this upside down A means for any vector W in R2, I can find a combination of U and V. In other words, I can find constants alpha and beta such that W is equal to alpha U plus beta V. So more generally, we write that a collection of vectors, V1 all the way up to Vk, span Rk if for any W in Rk, I can find alpha 1 up to alpha k, these are just real numbers, so that W equals the sum of alpha I Vi. And I can replace this Rk with anything I want, and this notion of span still holds. So instead of Rk, I could also write that V1 to Vk span V if the same thing holds. So this is what it means to have to span. Now let's look at these three vectors here, and I could add, let me add it in a different color. So I could add a few more vectors. And it's clear that all four of these vectors, let me call them W1 and W2, it's clear that if U and V span, then if I add more vectors, well, they continue to span. So W1, U, W2, and V continue to span R2, but on the other hand, they don't do it in the most parsimonious way. You can see that I only need two of those vectors to span. Moreover, you can see that any one of these vectors can be described by two of the others. So what we're trying to define here is this concept of linear dependence or linear independence. So let's define these precisely. A set of vectors v1 up to vk are linearly independent if there is no way to describe one of them in terms of the others. To describe one of them as a linear combination of the others. A simpler way to write exactly the same thing is as follows. If I do have some combination of them which adds to 0, so if I can find numbers alpha 1, alpha 2, all the way up to alpha k, so that this is equal to 0, the only way that this can happen is if all of the alphas individually are 0. So let's revisit our simple example from the previous page, where we had these two vectors, u and v. Note, how could I combine these to form the 0 vector? If it's true that alpha 1 u plus alpha 2v equals 0, rearranging this equation, that's exactly the same thing as saying that alpha 1u is equal to alpha 2v. And since I know that u is not equal to 0 and v is not equal to 0, this also tells me that alpha 1 and alpha 2 can't be 0. So I could divide. And this implies that u is equal to minus alpha 2 over alpha 1 times v. That tells me that u is a multiple of v, but it clearly is not a multiple of v. So it's not possible for this equation to be satisfied with non-zero alpha 1 and alpha 2. Therefore, the only way for this equation, alpha 1u plus alpha 2v equals 0, to hold is alpha 1 equals alpha 2 equals 0. So in other words, u and v are independent. This illustrates the more general definition of what it means for a collection of vectors to be independent. And finally, we need to define the concept of basis. If vectors v1 to vn are independent and they span Rn, then they form a basis for Rn. So this gets back to our thought, to our idea of a most parsimonious way to span a particular space. On the previous slide, we saw that we had 4 vectors that also span 2-dimensional space, but we didn't need all of those 4 vectors, but we needed just 2. A few operations that we're going to need repeatedly are the dot product and the outer product, and these have some important properties that we need to understand. So the dot product or inner product is defined and has various notations. So sometimes you'll see it u dot v, I should write. So u and v here are, again, in n dimensions. U dot v, or sometimes you'll see U transpose v under the convention that a vector, unless otherwise specified, is a column vector. And sometimes you'll see this with this bracket notation, uv. But in any case, it always means the same thing. It is the sum of I equals 1 to n. N is the number of coefficients that each one of these vectors has. ui, vi. And of course, note that this only makes sense if ui and vi have this, if u and v have the same dimension. And so all of this means the same thing. Outer product is, instead of writing u transpose v, we could write u v transpose when u and v are column vectors. So what this would look like is u times the transpose of a column vector, which is v. And this is now an n by n matrix. A really important property that we're going to use repeatedly is called the Cauchy-Schwarz inequality. And it tells us that the dot product of u and v is less than or equal to the length of u times the length of v. So let's use this opportunity to look a little bit more at the geometric property of what this operation really means. And let's do this with an example. So let's take the easiest two vectors that we know. A vector along what we like to call the x-axis and a vector along what we like to call the y-axis. So let's call this vector here 2, 0, and this vector 0, 2. One thing to note, of course, is that these are perpendicular to each other, and let's see what the dot product says. So let me call this u, let me call this v. u v is equal to u1 v1 plus u2 v2, which is 0 times 2 plus 2 times 0, which is 0. Perpendicular vectors have a dot product which is equal to 0. Let's just, so let's switch colors just so that we don't make this too messy. Let's try these two vectors. I'm also making these to be perpendicular. So let's try, let's call these x and y. So let's call x the vector 1, 1. Let's call y the vector minus 1, 1. And we can see that I'll use a different notation here on purpose. X dot y, the inner product between x and y, is equal to minus 1 plus 1, which is equal to 0. So perpendicular vectors have 0 inner product. In fact, the inner product is exactly related to the angle between two vectors, which we're going to see next. So we just saw that if u and v are perpendicular, then this is exactly equivalent to, I shouldn't put the if, u and v perpendicular is exactly equivalent to the dot product between u and v equaling 0. But in fact, something more general is true. And this doesn't have to hold only for two dimensions. If I call this angle theta between vector u and between vector v, then the cosine of theta is equal to the dot product of u and v, except I need to normalize for the length of u and v. Because note that here, if I double the size of u, remember the formula for the dot product, it's just going to double the size of that. Whereas if I double the size of u, that doesn't change the angle at all. So I need to normalize this by the length of u and the length of v. So this is a more general expression of what we just learned before, because if u and v are perpendicular, then the cosine is equal to 0. So this exactly tells us that u and v are perpendicular if and only if u and v have a 0 dot product, but it actually puts this in a more quantitative framework. What other operations can we do with two vectors? A very important one is projection. If I have this vector, sorry, I should starting it from the origin. Let me Let's try that again. If I have this vector, we're used to thinking about the projection onto the coordinate axis. And this is the projected vector. What is the expression for projecting one vector onto another vector? They don't have to be the coordinate axis. So let's think more generally here. I have a vector v, and I want to project it onto a vector u. You can see that I can do a better job at drawing that. Projection, I should have a right angle right there. So what is the expression for the projection of v onto u? Given vectors v and u, the projection of v onto u is given by, well, we know it's going to have to be somewhere on this line u. So it's going to be some multiple of this vector u. And the exact multiple is given by, again, the dot product. So this is a number. But this projection shouldn't be influenced by how big u is. U is just a direction that I'm projecting onto. So, and you can see that I'm multiplying by u here twice, so I want to divide basically by the length squared of u. So this is how we define the projection of one vector onto another vector. We can equally well project onto a subspace. Oops, a subspace spanned by, say, vectors u1 to uk. So I might want to project a vector v onto that subspace. If u1 to uk are each perpendicular to each other, and normalized, just to spare my notational, just to spare the extra notation of having to divide by the length of u as we did on the previous slide. So normalized means of length 1. Then the projection onto the span of u1 to uk of v is equal to v u1 times u1 plus v u2 times u2 plus v uk times uk. When k is equal to 1, this is exactly what we had before, but again, I don't have to divide by the length squared of u because I just assumed that it was equal to 1. So this is how we project onto a subspace. What about projection onto a convex set? This is a little bit more interesting, but something that's going to be very important for us. So let's draw a convex set. Of course, we haven't defined exactly what a convex set is. We're going to do this, but let's look at projection onto this set. So what does that mean? How do I project this point onto a convex set? Well, there's a few ways to define it. One natural way to define it is that the projection is the closest point in the convex set. So the closest point, just eyeballing it here, is something like that. And if you draw a line, you'll also notice something interesting, which is that if I carefully draw the tangent of this convex set at that point, this is a right angle there. So let's let this be my point u1, my point u2. I'm going to do the same thing with u2. I'm going to look at the closest point and look at its projection. And again, if I drew it carefully enough, then I should form an exact right angle there with a tangent. this space. So some important property that we should note immediately is that the distance between u1 and u2 is not expanded when I project. So it's less than or equal to, it's greater than or equal to, let me call the projection v1 and the projection of u2 v2. So it's greater than or equal to v1 minus v2. In other words, when you project onto a convex set, you can only bring things closer together. You don't have to bring things strictly closer together, but you can't expand them farther apart. And this is a property we're going to use extensively when we think about algorithms for constrained optimization. I've used this notation a few times without defining it, so it's time to define it and generalize it a little bit. So you may have seen me say the word length and write down, again, this is for x, a d-dimensional vector. You may have seen me write down this and call it length. Well, what this actually means is, so this is called the Euclidean length, or the Euclidean norm, and it's defined as follows. It's the square root of the sum of the individual components squared. So what is the relationship between this and Euclid? Well, this is just how we measure distances in our day-to-day lives. If I have a particular point, and I want to measure the distance from the origin, well, I can just measure this distance and this distance. And so suppose this distance is 3, suppose this distance is 4, then we know this distance has to be 5. How did we compute that? Well, we know that this distance of the hypotenuse is just the square root of 3 squared plus 4 squared, which is the square root of 25, or 5. And this holds more generally in general dimensions. Another thing you should note is that x dot product with itself is exactly equal to its Euclidean length squared. So we can generalize this definition from what's called the L2 norm to the LP norm. For p greater than or equal to 1 and less than infinity, xp is equal to the sum of xi raised to the p to the power 1 over p. The reason I need this absolute value here, and I didn't have it before, is that I also want this possibility for p odd. So if p is equal to 1, if I didn't have that absolute value, then the 1 norm of a vector 1 minus 1 would just be 1 plus minus 1, or 0. And it would really not be a reflection of any kind of length. Now you can note that I wrote p less than or equal to infinity. So you can consider what happens to this property as p gets larger and larger. But for now, I'll just define it at x infinity is equal to the largest in absolute value entry of x. In other words, it's the maximum over all I of the absolute value of xi. Some special properties of geometry when we measure distance with the L2 norm. So we already talked about the Pythagorean theorem. So what is the Pythagorean theorem again? It tells me that if I have two vectors that make a right angle, u and v make a right angle, then I know that u squared plus v squared is equal to u minus v squared. If the angle between u and v is greater than or equal to 90 degrees, then what happens? Let's change colors so we can see that. So if this were u, and this angle were bigger than 90 degrees, then what happens? So as I should have drawn u not to be longer. Let me fix that. So if u, whoop, thank goodness for technology. So let's draw u. So u is the same length. I've just rotated it out so that the angle is bigger than 90 degrees. And we can see that if the angle is bigger than 90 degrees, then what happens to this inequality? Which side gets bigger? Well, you can see. It's just the hypotenuse here is going to be stretched out. So it's the right-hand side that's getting bigger. And u squared plus v squared will be less than u minus v squared. And of course, if the angle is less than 90 degrees, then the reverse happens. So this is generalizations of the Pythagorean theorem. The triangle inequality does not care about the square of the norm, but actually just tells us about the norm as a distance of measure. And the triangle inequality says something very, very simple and natural to us. Basically, the distance between 2 points, the straight line is the shortest distance between 2 points. And if you visit any third point, then going this way is actually going to be longer than going directly. So again, it's important to note that the presence of the square changes this relationship quite a bit. So to write it differently, if this is x, and this is y, and w is any point, then the distance between x and y is less than or equal to the distance between x and w and the distance between w and y. And this is true for any of these LP norms, and this is true for any vector w and any vectors x and y. We're going to be using these properties. It's useful to have them at your fingertips for many of the calculations that we'll be doing. Okay, a few more things now, more specific to matrices. We're going to be talking about a matrix M. That's M by N. Oops, I drew it as square, but here's M, this is M, and this is N. And very often we will be talking about square matrices. The null space of a matrix M is all the vectors which it sends to 0. So it's all x such that M times x is equal to 0. The range of M is all vectors that it maps to. So it's all y equal to mx for some x in Rn. The rank of a matrix is equal to the dimension of the span of the columns, which is also equal to the dimension of the span of the rows of M. And if M is n by n, then the rank of M is equal to n exactly when, if and only if, the determinant of M is equal to 0. And this is true exactly when the null space of M is equal to the 0 vector. And this is exactly only the case when the range of M is all of Rn. So these are 3 properties that it's very handy to have at the tip of your mind. So if the determinant of M is equal to 0, then we know that one of the following must be true. Then the columns of M cannot all be independent. Note that determinant only is a calculation that makes sense for square matrices, so only in the case where M is n by n. And Also, the rows of M cannot all be independent. We talked about a subspace a little bit in the previous slides. So a subspace, here's an example of it. If I have three-dimensional x, y, z space, the span of x and y is a subspace. V, in general, is a subspace if it's closed under addition and scaling. It's also important to define an orthogonal complement of a subspace. For V a subspace, its orthogonal complement is all vectors that are perpendicular to it. All W such that W dot product or inner product with V is equal to 0 for every V in V. And we'll see some analogs of this definition when we talk about convex sets and cones. An affine subspace is just a subspace translated by a fixed vector. These are important definitions just to keep in mind in case you see them, just so you know what we're talking about. That is really the only reason to have to go through and define certain specific definitions like this. Symmetric matrices play an important role in convex optimization, and it's something that we have to understand in careful detail. First of all, for a matrix M to be symmetric, it has to be square. So if M is an n by n matrix, then it's symmetric if it's equal to its transpose. In other words, if the ijth element of M is also equal to the ji element of M. Symmetric matrices have some very important properties. So let me first define what an eigenvalue and eigenvector is. Lambda v is an eigenvalue eigenvector pair for M if mv is equal to lambda v. So for example, if M is equal to this vector, to this matrix 1, 1, 1, 1, then you can check that the vector v and lambda equals 2 is an eigenvector eigenvalue pair. You can also check that the vector v is equal to 1 minus 1 and lambda equals 0. Lambda equals 0 is also an eigenvector eigenvalue pair. A key fact that we need is that all eigenvectors of a symmetric matrix are perpendicular to each other. And this is very special. And all eigenvalues are real. So note that this doesn't always have to be the case if we don't have a symmetric matrix. So for example, if M is the non-symmetric matrix, which is 0, 1, minus 1, 0, check for yourselves that the eigenvalues are not real. And of course, M is not symmetric. So if M is symmetric, then we can always write M is equal to the sum of lambda I times VI transpose, where lambda I VI is an eigenvalue eigenvector pair for M, and also where VI is normalized. In other words, it has length 1. This is a very important property that we're going to use in a number of computations. We'll do this in the next slides. And it's sometimes called the eigenvalue decomposition or spectral decomposition. Of a matrix M. And it's something that we're going to use quite a bit. So we know that if a matrix M is, so let's write what we had before. So M symmetric means that I can write M as a sum of lambda I, that's an eigenvalue, VI transpose. Note that this is, maybe this is bears commenting a little more. So what is VI transpose again? We saw this a few slides ago. VI transpose is the outer product. This is the outer product. And if each VI is an n-dimensional vector, this is an n by n matrix. Which makes sense. It's saying that I can write M as a sum of n by n matrices. If all the eigenvalues are greater than or equal to 0, then M is in addition called positive semidefinite. So if M is symmetric and all of its eigenvalues are greater than or equal to 0, then M is called semidefinite. So let's see why this is important for us. So first of all, let's check a particular property of semidefiniteness. So what this statement says is that a matrix A, an n by n symmetric matrix, I won't write it all out, is positive semidefinite, PSD for short, if and only if the quadratic it defines is everywhere non-negative. So what is that? Let's write that in symbols. So this is saying A is PSD. This is equivalent to writing that A is equal to sum of lambda I VI transpose, where lambda i's are non-negative. We just said that on the previous slide. And this is also equivalent to writing that X transpose AX is greater than or equal to 0 for every X in Rn. So this is the content of what this statement is saying. So let's actually take this opportunity to do this, to see how we can use properties of semidefiniteness. So let's show this. So this takes a little bit of calculation, but it's good practice. So how do we go about it? What do we have at hand for us? We need to plug in every single X and check that we have non-negativity. So that obviously, we can't do that one at a time. In fact, I haven't even told you what the matrix A is. I've only said that A has this expression here. So this is the only thing we need to go on. So let's work from there. So I know that the VI's are perpendicular. Well, that also means that they're independent, and therefore they span all of Rn. So if that's the case, then I could write a generic element X in terms of that basis. So let's write x in terms of the basis v1 to vn. What does that mean? Well, that means that I know x is in there somewhere. v1 to vn spans all of Rn, so that means that x is equal to, for some choice of constants here, sum of, I'm just going to call them alpha I to keep it generic, alpha I vi, for some choice of alpha I. So now let's actually do this calculation. X transpose AX is equal to the sum of alpha I vi, that's x. Now I'm going to write A using this expansion here. I'll use a different index of summation. I'll sum over j, so we don't get confused. Lambda j, vj transpose. And I need another x. I'll use a k in this case. This is equal to alpha k times vk. So let's start combining these and using properties of v's, namely orthogonality. So this is equal to, I'm not going to mess with this left-hand side at all right now, so this is still sum of alpha I vi. And now this is a sum over j and sum over k, so let's do this simultaneously. This is a sum over j and k of lambda j, alpha k, vj, vj transpose, vk. You see what happened? I moved this alpha because it's just a constant. I moved it all the way left. We need to make sure that we don't change the order of operation of any kind of matrix multiplication, because those don't necessarily commute. And now, what do you see here that we defined at the very beginning of this lecture? This is just the dot product. This is just the inner product between Vj and Vk. But Vj and Vk are perpendicular. This is the magic of A being symmetric. Since these are perpendicular, this is equal to 0 if j is different from k, and it's equal to 1 if j is equal to k. So okay, we got the 0. That's because they're perpendicular if they're different vectors. But if it's the same vector, why is it equal to 1? We need to synthesize a couple things that we've seen in this lecture so far. So if it's the same, Vj transpose Vj, remember that was one way to write the Euclidean norm squared. It's the length squared. But these are all normalized. They have length 1. So that basically completely goes away. And what we have is that this is therefore equal to what I have on the left, which I didn't mess with, alpha I vi, times not the sum over all j and k, but only the ones that are equal. So I'll just keep one of those parameters, j, and I've got lambda j, alpha j, vj, because this turned into 1. And now you can see we're going to play exactly the same game. I'm going to combine this. This is equal to the sum over I and j of alpha I, alpha j, lambda j, vi transpose, the vi transpose here, times vj. And again, we have the same game. Vi, vj, it's equal to 0 unless I is equal to j, in which case this is 1. So this is just equal to the sum over I of lambda I, alpha I squared. What do we conclude? We know that A is positive semidefinite, which means that all of the lambda i's are greater than or equal to 0. Alpha I was just some weights that I picked to describe to describe x. I don't know if those are non-negative, but it doesn't matter because I have the square. So we can see that this is always going to be greater than or equal to 0. Okay, so this is how we used, the reason for doing this calculation is not only did we see that this, in fact, that star holds, but also it gives us a little bit of a sense of the power in terms of calculation of what we get when we have this eigenvalue decomposition in terms of perpendicular vectors. It's easy to check that for any matrix, square or not, A transpose and A transpose A are always positive semidefinite. How do we check that? Just using the previous fact. In other words, all I need to do is check that X transpose A transpose X is greater than or equal to 0 for all X. But you can see that this is exactly equal to A transpose X squared, because this is just of the form V transpose V, which is the Euclidean norm squared. So certainly this is greater than or equal to 0. And similarly for A transpose A. So we got this nice property about the eigenvalues and eigenvectors just by this simple fact that we derived in the previous page. Maybe not so simple. It took us a little bit of calculation. So that's all we're going to need for linear algebra. A few more points here about multivariable calculus. We're not going to define continuity precisely because most things that we see are going to be continuous. So basically, anything that doesn't have a hop like this is not continuous. But we're allowed to have things that are smooth, things that are pointy, so this is continuous. An important thing to define is this technical term called Lipschitz continuity. So a function f of x is called Lipschitz continuous if f of x minus f of y, the amount that f changes when I go from x to y, is controlled by how far away x and y are. So this is saying that if x and y don't change very much, then f of x to f of y can't change very much. So we're going to see this. This is going to come back for us. And finally, we need two simple generalizations of the first and second derivative. So if f, again, is a map from Rn to R, in other words, f of x is equal to f of x1 to xn, then the gradient of f, which we've already seen a number of times, is just the vector of partial derivatives. And the Hessian is a generalization of the second derivative. This is an n by n matrix where the ijth component is the second derivative of f with respect to xi and xj. And finally, it's just useful to make sure that we know how to calculate the gradient and Hessian of a quadratic. So suppose f of x is equal to x transpose qx plus q transpose x plus c. This is a generic quadratic in n variables. Then the gradient of f of x is equal to the very, very similar rules to what you remember from baby calculus. And the Hessian of f is just equal to q. We're going to need other concepts for sure, but we're going to develop them as we need, or I'll provide some references. The main thing that we're going to need, and the main thing that I know from my experience of teaching this class many times to many students from different departments, is that linear algebra is the sticking point. Linear algebra is the thing that we can never get enough of. And I have a few references here that I recommend. Of course, if you have your favorite book, by all means use that. There's a recent book called Introduction to Applied Linear Algebra. That is a softer introduction and very nice. The book Convex Optimization also has a material in there, has an appendix, and along the way develops a lot of linear algebra tools. I like these first two books. For one thing, they're both freely available to you, and will always be that way with arrangement with a publisher. Another great book that goes much more in depth, probably more in depth even than we'll need, but a book that I found useful is the last one that I've written down here. We'll pick this up next time.